Hi everyone, this is Irma Kaikan from the University of Arizona, and today I'm going to present our paper MAMBA, a multi-arm bandit framework for beam tracking in millimeter wave systems. And this is a joint work with Dr. Berkat Gün, Dr. Minji Fang, and Dr. Marwan Kruns. So we know that there's an explosive increase in the number of connected devices. In fact, the recent poll shows that average US person has about 11 connected devices, which means that in US alone, there are over 1 billion connected devices, which is a huge number. This, of course, means that there's a growing demand in the mobile broadband data as well, and other requirements that these devices might have, such as low end-to-end latencies. And that's why next generation wireless standards, such as 5G and 802.11ad and AY, rely on millimeter wave bands, as these bands have abundant spectrum availability to meet these requirements. However, millimeter wave also complicates certain control functions, such as initial access, by which a base station and the user equipment establishes the very initial connection. And in the current 4G LTE systems, initial access is performed by an omnidirectional signal called cell reference signal. But if we were to do this omnidirectional approach in a 5G millimeter wave system, the range that we would get would be very low due to the large path loss experienced by those millimeter wave signals. That's why in 5G, even the initial access needs to be done directionally to achieve the full potential of these systems. That, of course, means that whenever a new UE enters the system, or whenever a UE moves within the cell or from one cell to another, this incurs a large overhead to the system. So today we will be focusing on the beam tracking, and we will look into designing intelligent beam tracking techniques. So the goal of an intelligent beam tracking method is to provide fast recovery from connection losses, whether they being due to mobility or blockages and etc. And in 5G NR, beam tracking is done by using frequent SS bursts or beam sweeps, which of course adds an overhead to the system and lowers the throughput. So the more frequent the SS bursts are, the more reactive the system becomes, but of course it means that also there's a larger overhead. So what we are aiming to do here is to lower this overhead and increase the time between two consecutive beam sweeping rounds and update the beams during the data transmission period. So this would, of course, reduce the latency because a lost connection can be reestablished faster before actually waiting for the next beam sweeping round. And it would also improve the throughput. And we are looking into coming up with a one-fits-all model-free solution, meaning that we will be doing no assumptions on temporal channel models and or user mobility, etc. And we're also looking into designing a low-complexity solution. So here is what we do. We assume that the initial access has already been completed. So the base station has already some idea about the qualities of various beams. And we also assume that it's actually a fact that the UE has wider beams. So we're looking into the problem from only the base station's side, because it's very likely that UE will not need to change its beam until the next SS burst. So now the base station and the user equipment has some initial connection, but let's say the UE has moved. So now the base station has a bunch of other beams that it can select from to either reestablish the connection or improve the quality of the connection. So here's how we formulate this problem. The base station has a bunch of actions that it can select from. Let's number them from 1 to k, and these actions actually correspond to different beams. And each beam I has an associated reward distribution, theta I, at time t. And let's suppose that beam I, let's suppose that the base station selects beam I at time t, and it observes a reward RT from that beam, which could be, this reward could be data rate, for instance. It means that this reward is sampled from the distribution capital theta IT, where the mean of this capital theta IT is denoted by this lowercase theta IT. And you can probably see where I'm going with this. This is actually a multi-arm bandit problem's definition. And the solution that we are proposing here is to solve this problem using reinforcement learning. So here, basically the lowercase theta theta are also modeled as random variables, which we use as a tool to kind of like approximate the true means of those distributions, those reward distributions. And the multi-arm bandit problem captures the trade-off between exploration and exploitation. And we are using reinforcement learning to solve this multi-arm bandit problem with the goal of minimizing the regret, which is the deviation from an oracle policy, which can always find the best action at each time slot. So to briefly recap, before we go into more technical details, the problem that we are trying to solve here is that how can we find the best beam and rate to be used along that beam for communication at each time slot? And our goal is to maximize the cumulative throughput until time t. So Thompson sampling, as I just said, uses a technique called Bayesian inference. So we need some prior reward distribution associated with each arm. Then we know that these prior means or this prior information can be gathered through initial access, which has already been completed before we start our beam tracking technique. And then what we do is whenever an arm is played or whenever a beam is selected for transmission, we observe a reward and we then update this beam's reward distribution. And then we simply select a new arm according to the updated posterior distributions. So now let's go into more of the details of our model. So the reward distribution that we use should account for multiple MCS indices because we're going to be doing rate selection as well. And that means that the reward distribution that we use needs to be multi-dimensional. So a suitable reward distribution here is the categorical distribution, which is a generic distribution. And actually, it can be used to model any discrete random variable. So in our case, our categorical distribution will be m-dimensional, which corresponds to m possible outcomes. So it could mean a transmission failure or satisfying one of the m-1 MCS indices. Then we need to select the prior distribution of thetas, as I mentioned, because we're going to be using Bayesian inference. And for that, and these will be updated continuously, and hopefully, as time goes to infinity, these will approach to the true means. So for that, we have selected Dirichlet distribution as the prior, since it's the conjugate prior of the categorical distributions, which means that this way, the posterior at each round after we update those priors will also be Dirichlet distribution. And we will end up with the simple linear update rule, as you can see here. So the update rule basically tells us that if a beam I is selected as the action at time t, is selected as the action time at time t, we will update its distribution by simply summing the Dirichlet distribution's parameter alpha it with the observed reward vector. And if it's not selected as the action, we will simply not update its distribution. And here, this vector r, the reward vector r, simply contains a single one on the entry corresponding to the highest achievable MCS index, and all other entries will be 0. So what I've just described is valid for a stationary system. But in case of a non-stationary system where the means themselves can change in time, we need some modifications to keep track of these changes. So in this case, Thompson sampling is still effective, but we need the update rule to be adjusted slightly. And what I mean by that is we introduce two new variables, gamma1 and gamma2, and we use them as follows. So this time you can see that this update rule is pretty similar to the one before. But in this case, what we do is if beam I is not selected for transmission, we will simply forget, we call this parameter gamma1 the forgetting factor. We will simply forget some of the old information. And if beam I is actually selected for transmission, in addition to forgetting some of the old information, we will boost the reward by another factor called gamma2. So what we do are the two things. First, we forget some of the old information by a factor gamma1, and we boost the new information by a factor gamma2. So that's the slight adjustment that we need to make. So far I have described how we update those distributions. Now let's move on with how do we decide the arm or the action at each time. So as I said, we do that by Thompson sampling. At the beginning, we said that we need to balance exploration and exploitation. So one way to do that is to do a technique called probability matching. Or in other words, arms with higher mean rewards need to be more likely to be selected, but they should not be always selected, because if we select them all the time, it becomes a greedy approach, which is not optimal. This is actually not balancing the exploration versus exploitation. This is meaning that we're always exploiting the current information. So to do probability matching, we can do Thompson sampling, which Thompson sampling basically does is it takes a sample realization from each arm's updated reward distribution. So in this example, for instance, I'm showing a three-dimensional Dirichlet distribution as a heat map. So the red corresponds to higher probabilities and darker blues correspond to lower probabilities. So for instance, this distribution is likely to generate a sample like this, this SIT, which is, in this case, it's three-dimensional, which could mean a transmission failure, BPSK and QPSK, for instance. So let's say that the sample is failure equal to 0.1, BPSK equal to 0.2, and QPSK equal to 0.7. So then for each arm, what we do is we compute this number. We basically multiply this SIT by a vector called vector V, which is what we call a value vector that contains the rates associated with each MCS index. And what Thompson sampling does is basically it selects the action that maximizes this multiplication SIT times V. Which basically tries to balance out by not always using the mean instead of SIT. It takes a sample, so arms with lower means also have some chance of generating a higher sample, and they have some chance of being selected as the action. So after selecting the beam, then we need to select the MCS index to be used along that beam. And since we already have a sample from the selected beam, let's call that beam I star. Let's call that sample SI star. So for the rate selection, we propose two methods. The first one is a greedy method, which basically selects the MCS index with the highest expected reward, even if that MCS is not very likely to be attained. So it always looks at the expected reward. So let's say 64 QAM, for instance, has a chance of being attained. Let's say it has 10% chance of being attained, but the associated reward with 64 QAM is very high. So greedy rate selection may actually decide to go with 64 QAM. And then we have the conservative selection, which in contrast selects the MCS index that's most likely to be attained, regardless of its associated rate, as long as it's non-zero. So now let's move on with the performance evaluation. This is a cartoon representation of our setup where we have a host PC that is connected to a signal generator with a phasor antenna that represents the base station. And we also have a spectrum analyzer with a horn antenna that represents our user equipment. So here the base station, and we have discrete measurements points, which I'll explain in a minute. And here the base station transmits the signal and the host PC reads the power from the spectrum analyzer, and that kind of like emulates the effect of the hybrid IRQ packets. And then basically this host PC tells the base station which arm to select next. And these measurements are taken from discrete points. That means that the UE is moved from one point to another. And this entire procedure of transmitting the signal and reading the powers are repeated simply because of the reproducibility of the results. And these are what the actual setups look like. So we have made experiments indoors, outdoors, with and without reflectors, as well as with and without blockers. Now let's talk about some sample results. So in the first figure, we show the total delivered traffic versus time. So here we have a dynamic oracle, which can always select the best beam and rate. A static oracle, which is basically what's kind of like what 5G is proposing. So we find the best beam and rate during IA and keep using them until the next SS burst. And we also have ATS, which is the Thompson sampling method that uses the non-stationary update rule that I described a couple slides ago, with the conservative and greedy rate selections. So as you can see here, the ATS for both the conservative and greedy rate selections significantly outperforms the static oracle, and it performs actually pretty close to a dynamic oracle even as the time goes on. So if you look at the second figure, you can see how the average data rate changes versus different UE speeds. And as we expect, you can see that the performance decreases as the user starts moving faster and faster, both for the static oracle and also for the ATS. But what's important here is that on the left side of the figure, for RX speeds less than 10 centimeters per slot, you can see that the ATS's performance is very, very close to a dynamic oracle. And actually, if you do the math, this 10 centimeters per slot means that 360 kilometers per hour. So it's very, very likely that almost always a UE will be moving slower than this number. And in the last two figures, we are seeing the effect of gamma 1 and gamma 2 on the average data rate. So you can see that the performance of ATS depends heavily on the selection of gamma 1, but as long as it's not selected very low, meaning that all the information is almost instantly forgotten, or very high, meaning that all the information is never forgotten. So for any number between those two, we'll say from 0.2 to 0.8, the performance of ATS is still pretty good. And for gamma 2, we can see that as long as gamma 2 is larger than about 10, we can see that the performance of the ATS pretty much remains the same. So to sum up, we have developed an efficient and practical solution for user tracking in mobile millimeter wave systems. And we have analyzed the regret bounds of the proposed method and also studied its performance with simulations and hardware experiments for a complete evaluation. And one final note, so the data sets of the experiments that I have mentioned here are available in our website, wireless.ec.arizona.edu. So if you're interested, please check it out. And with that, I conclude my presentation. I would be happy to take any questions online or offline.